Greetings. So welcome to today's class. So if you recall, we were looking at the state space realization, right? We were looking at the equivalence between the transfer function and the state space realization, and we were also looking at how to write the state space realization in the first place, right? So, and we also saw that, like when the transfer function representation is typically unique, the state space representation is non-unique. We can have an infinite set of state space realization for a given system. So essentially, we are going to start with that concept in today's session. So that we are going to start off with a question, right? How does the state space realization of a system change under a transformation of state variables? So depends on how we choose the state variables. So depending on the choice of the state variable, the question is, can we comment, like as to how the state space representation is going to change, right? So that's the first question we are going to answer in today's class. To answer that, let's consider an example, right? So what do I mean by this transformation of state variable? Okay, to begin with. So let's consider a simple example. So let's consider a second order system where the first state variable, let's say, is the output y of t, and the second state variable x2 is the first time derivative of the output, let's say y dot. Okay, so these are the two state variables. Okay, so these two state variables completely characterize the system. Now, let us say that we define two new state variables, let's say z1 of t, to be equal to y of t plus y dot of t. Of course, one may wonder if y is displacement and y dot is speed, like what physical quantity is characterized by this z1, right? So that's also another feature of state space representation. That is, the state variables need not necessarily have a physical meaning, okay? Which is also something we need to remember. And let's say we define z2 as y dot yt minus y dot t. Okay, I'm just taking these two as the new state variables. Then, if we formulate the new state vector z1t and z2t, what will happen is that, like, it will take the form something like this. That is, it will be one and minus 1. So you can see that if I write it in terms of x1 and x2, z1 and z2 will become like this, right? So if you do this matrix vector multiplication, we get z1 and z2, right? So I'm sure all of us can immediately agree with that, right? So now this vector is the new state vector. Let's say z. We call it as the vector zt. This was our original state vector x of t. This matrix, in this case, is a 2 by 2 matrix. In general, it is a n by n matrix for a nth order system. This matrix is a transformation matrix, okay, which transforms x of t to z of t. Okay, so that's why it's called as a transformation matrix. All right, so that is the what I say, transformation. Okay, that's what we mean by what happens when there is a transformation of the state variable. Okay, so this is essentially a transformation of the state variable. Okay, so that is like we start off with a state vector x. So what we are doing is that, like, we are transforming the state vector by multiplying by a matrix T, which is a transformation matrix. And then like we are asking the question, in terms of the new state vector, what happens to our state space representation, right? So that's what we are going to answer. So let us consider our standard state space representation, which is given by x dot of t is equal to axt plus BUT. Let's say we consider the multi-input, multi-output system. Okay, so this is our state equation in that case. Then our output, becomes y of t, which is also a vector that is going to be equal to cxt plus du. Right? So that's our state space representation for the MIMO system, right? So is it not? So now, if we consider this, we essentially want to figure out what happens to the state equation. Okay. So what we do, we consider the transformation of state variables such that the new state vector z is some t times x of t, where the matrix T is invertible. Okay, so that's how the transformation matrix is chosen. Okay, so we essentially consider the class of invertible matrices. Okay, there are infinite of them, so that's why there are infinite possibilities for state transformation. Okay, so then we can immediately see that x of t could be written as t inverse z. Okay, so that's what will happen. All right. So that's the inverse transformation. All right. So why am I saying there are infinite such t's? Let me give a simple example. Let us say we take t. Okay, just as a simple example. Let us say we take t to be some scalar times identity matrix. Right. T being some real number. Right. Even this simple transformation matrix, which is invertible, right? Because what will be T inverse? T inverse will only be 1 by C identity. Of course, C is not 0, right? That is important. Okay. Now, all of us will agree that there are infinite such C's, right? So, because C is a real parameter, so there is an infinity of them, right? Is it not? So, immediately we can observe that we are going to have an infinite number, right, of such transformation matrices, right? So let us say, we apply some arbitrary invertible transformation matrix T, right? And we see what happens to the new state equation or the modified state equation. So we are going to look at z dot t. If I take z dot t, that's going to be equal to capital T times x dot of t. And what is x dot of t? We get from the above state equation. That's going to be t times axt plus but. So once again, please stop me wherever there is a question. Okay. So if we multiply throughout, this comes out to be taxt plus dut. However, we know that x of t is nothing but T inverse ZT, right? So what will we get out of this? This will be T inverse Z of T plus TV U of T. Okay, so this is what we have here. Okay, so what happens is the following. Okay, so we essentially have this new state equation to be Z dot T to be equal to TAT inverse times Z of T plus TPU of T. Okay, so that's what happens. Okay, so this is the modified state equation, okay, or the transformed state equation, right? So, course, the system is the same. Okay, just that the choice of the state variables has been changed, right? So now what happens is that this is the new state matrix T8 inverse, and TB is the new input matrix. Okay, so if I put TB around parentheses around TB, that's going to be the new input matrix. Okay, so that is the difference here. Okay, so as far as the state equation is concerned. So what will happen to the output equation? We just need to substitute x equals t inverse z into this equation, right? So the output equation will become y of t will be equal to t times t inverse zt. Right, I'm only substituting for x as t inverse z plus d times u of t. Okay, so the new output matrix is going to be the c times t inverse. Okay, and this is the transformed output equation. All right, so this is the transformed output equation. So put together these two equations. Okay, is the transformed state space representation. All right, so that is the transformed state space representation. Let's call these two equations using some Roman number numeral 1. Okay, so that like we are going to use this equation as we go along in today's discussion. So what happens is that what is the answer to the question that we started off with? How does the state space representation transform, right? When we or change when we have a transformation of state variables, it changes like this. That is, if we had a state space realization ABCD, it changes to the realization TA T inverse, TB, CT inverse, and D. Okay, so this is the transformation. Okay, which happens. Okay, so when we define z of t to be some t of x of t, where t is invertible. All right. So such a transformation is what is called as a similarity transformation. Okay, so that is, what is a similarity transformation? Let's say we start off with a state space realization ABCD. We apply z of t to be some t times x of t. We get a new realization TA T inverse, TB, CT inverse, and D. Okay, so now this new realization, what we have obtained, is an alternative state space realization of the same system, and this such a transformation between these two state space realization is what is called as a similarity transformation. Okay, so why is it called as a similarity transformation? I'm going to leave this to you as an exercise. What is similar between the two state space representations to this transformation? It so turns out that the eigenvalues of the original state matrix A and the transformed state matrix TA T inverse are the same. Okay, so I hope all of us recall what is the definition of an eigenvalue and an eigenvector, right? So the pair lambda v is called the eigenvalue and the eigenvector if for a non-zero vector v, a times v is equal to lambda, right? So that is when we have lambda to be an eigenvalue of a and v to be the corresponding eigenvector. And if we recall how we calculated the eigenvalues, we solved this equation, determinant of lambda a minus a equals 0, right? If we recall, we discussed these a few classes ago, right? We get a minus lambda I v equals to 0, and since v is non-zero, a minus lambda I is singular. For a singular matrix, the determinant is 0, right? So that's why that's how we get this equation, right? Determinant of a minus lambda I to be equal to 0 as the equation that we need to solve to obtain the eigenvalues of a matrix A. So, as far as this transformation is concerned, it is called as a similarity transformation. And if we ask the question as to what is similar about this transformation, the answer is that the eigenvalues are the same. Okay? The eigenvalues of the original state matrix A and the transformed state matrix A P inverse remain the same. So that's why it's called as a, in that sense, it's called as a similarity transformation. And another definition that we need to be aware of is that like what is called a spectrum of a matrix. So what is the spectrum of a matrix? The spectrum of a matrix A is represented by sigma A. It is nothing but the set of eigenvalues of it. Okay. So let us say we have an n by n matrix. We'll have n eigenvalues, right? So the set of those n eigenvalues is what is called as the spectrum of the matrix. Okay, so that is another definition that we need to be aware of. Okay, so these are all some terms that we will use as we go along. All right. Okay. So now we are going to ask ourselves the next question. Okay. So the first question we asked today was that like what happens to the state space representation when we have a transformation of state variables, right? Now the second question we will ask ourselves is that like what happens to the planned transfer function under a similarity transformation. Now the question is that like one may wonder, hey, what is the relationship between these concepts and automotive control, right? So you'll see them as we do more case studies and so on. Okay, right now we are learning this theory. We'll see that sometimes, like the equations that we get, need to be transformed for processing, and that's where these similarity transformations are helpful, but we should essentially get some concepts cleared up, right? So that's why I'm discussing the basic theory behind them, right? So what happens when we have a similarity transformation? So now, in order to answer this question, of course, we are going to stick to the memo system. So please recall that for the memo system, we have what is called as a state transfer function matrix. Function matrix P of this is going to be C times Si minus A inverse B plus D. Okay, so that is going to be the transfer function matrix for the memo system. Okay, so now what we will do is that like we will follow the same process for the new state space representation, right, which is given by equation Roman numeral 1. Okay, we have the transformed state equation and the transformed output equation. So what we are going to do is that like we are going to take the Laplace transform of these equations, and then like we will get the corresponding transfer function, right, and we will see how the transfer function changes, okay, under the transformation of the state variable. Okay, so let us take the Laplace transform of 1. Okay, the equation is now Roman numeral 1. Okay, so once again, I'm just going up. Okay, so what is that Roman numeral 1? It was the transformed state equation and the transformed output equation, right? So those are the two equations. Okay, we are going to take the Laplace transform of these two equations. Okay, so please keep this in mind. So going down, so if we do this, so what we are going to get is that like, since by now all of us are familiar, I'm just going to write down the steps as far as the Laplace transform is concerned. So we will get S prime capital Z of S minus Z0. That will be equal to EA, sorry, T inverse Z of S plus E times D U of S Okay, that is the first equation. Of course, when we want to find the transfer function, we take all the initial states to be 0, right? So it need not be 0 in general, but that's the process of deriving the transfer function, right? So what happens here? So if you collect the terms involving Z, you'll get Si minus TAT inverse Z of S will be equal to T times D U of S. Okay, so that's the equation we will have. Okay, so from here we will get the vector Z of S to be equal to Si minus T inverse, the whole matrix inverse, right? So we are inverting Si minus TAT inverse inverse, sorry, Si minus TAT inverse, taking the inverse of that, so we get TB U of. Okay, so that remains. So this will be Z of. So please follow the mathematics. Okay, so this will lead to an interesting result. Now taking the Laplace transform the output equation, you'll get Y of S, which is nothing but C T inverse Z of S plus D times U of S. Okay, so this will be C T inverse. If you substitute Z, you will get Si minus A, T inverse inverse, then T B U of S, okay, plus D times U. Okay, so now, of course, I'm going to leave this as an optional exercise to you. If you use matrix algebra, okay, you will see that I'm not going to do this mathematics here, but I leave it as an exercise for you to do. One can show using matrix algebra that this is nothing but Si minus A. Okay, this complex looking matrix boils down to Si minus, sorry, A. Okay, so that's what it boils down to. Okay, so consequently, what will happen? We get something which is interesting, right? This implies that Y of S will now become, sorry, not this entire thing, sorry. I'm sorry about the confusion. I should draw the brace very, very carefully. It is starts after C and then like it goes before D. Okay, sorry, not before D, till 1 minute. No, starts from T inverse, then like goes to D. Correct. Yeah, this transforms to Si minus A. That is T inverse times Si minus T inverse times T. Okay, that is nothing but Si minus A. Sorry about that change. Okay, so that's what we have. So consequently, what will happen is that the output will still remain S times, sorry, C times Si minus A inverse D plus D multiplying U of S. Okay, and this becomes the Planck transfer function matrix. And so consequently, the interesting observation that we can make is that the Planck transfer function matrix or the transfer function remains the same, okay, under a similarity transformation. Only the state space representation changes, but no matter what is the transformed state space representation, the transfer function, right, in essence remains the same. Okay, so these are interesting points to note. Okay, so let me write down these points. Okay, the transfer function or the system transfer function or the Planck transfer function remains the same under a similarity transformation. Okay, this is first point. All right, and we can immediately sort of like what to say, uh, sort of understand now that there are infinite state space representation, because as we just discussed, we can have an infinite number of choices for t, right, that are invertible, right? So there's an infinite state space representation, representations of a dynamic system, but there is only one transfer function, only one transfer. Okay, the transfer function is unique. So we have sort of like generally proven that statement also, right, by looking at the similarity transformation. So what does this mean? So let's say there are 15 offers, like we take a problem, we take a physical system, and then like we derive the equations and we find the transfer function. All 15 offers will get the same transfer function if we had the same governing equations to begin with, right? But each one of us can get a different, can write on a different state space, right? That gives us some flexibility. So this essentially tells us that the state space representation is non-unique. Okay, so this is very important. Okay, so state space representation is non-unique. Okay, so for the same system, we can have an infinite number of state space representation. Okay, so this brings in some interesting features and advantages, which we will appreciate as we learn more, right, on state space based analysis and control and so on. Okay, so but right now, like please remember these facts. Okay, so those are important, right? Okay. Fine. Any questions before we go forward? Okay. So I am going to give you the corresponding tasks as exercises. So, yes, any question? Yes, Bhaskar.
We were discussing in schedule of canonical forms. So, is that related to this point?
I'm sorry, can you repeat the question? I could not hear you.
Yesterday, you were discussing on canonical forms. So, whether this is related to that canonical forms?
So, we are going to learn a few canonical forms, okay? And you can transform between canonical forms using appropriate transformation, okay?
Okay, yeah.
All right. So we are going to learn a couple of canonical forms as we go onward. All right. All right. Okay. So any other questions? Okay. So I'm going to give you a couple of exercise problems to do. You need not submit them as a homework, but please do try them out. Okay. So the first exercise is that, like, of course, the exercise problem is for a CISO system. So if you consider a CISO system, what I want you to show is that under a transformation of state, the base realization is A, B, C, D, where A is a matrix, B and C are vectors, and D is a scalar. Okay. When we transform Z of t to be equal to t times x of t, the new state space representation or state space realization becomes TA T inverse T times the vector B, T inverse times the vector C, and D. Okay, so this is an exercise I want you to do. All right, as far as CISO system is concerned, and also show once again in the CISO case that the plant transfer function remains the same. Okay, so the plant transfer function remains the same. under a similarity transformation. So of course, it will remain the same. I just want you to just follow the same exercise once again, so that like you can convince, right? Yeah. So if you recall, what was the plant transfer function for a SISO system in relation to the state space representation, C dot Si minus A inverse B plus B. Okay, you need to follow a similar process. You would get the corresponding what is it? Transform state space realization, right? Take the Laplace transform of the transform state space realization and evaluate the transfer function. You will see that you will get the same answer, right? So that's something which you can be done as an exercise. So please try that. Okay. All right. So now moving on. So we are now going to, having seen what is the state space representation and some properties associated with state space representation. So let's apply it to our course, right? Because our course is on control of automotive systems, right? So in general, any control design, if you recall, we focus on stability and performance, right? So these are two important attributes associated with any control design, right? And if we recall, when we did control design using transfer function, we use the notion of Debye stability, right, or bounded input, bounded output stability. So what is this notion of Debye stability? This notion essentially sort of indicates that the output of the system should remain bounded for all possible bounded inputs and all time, right? So that's the notion of Debye stability. An alternative notion, right, of stability that we are going to use in this particular course is one of stability of an equilibrium state. Okay, so we will see what is the equivalence between the two as we go along. But at this point, when we are dealing with the state space representation, we are going to introduce or get introduced to this alternative notion, right, of stability, with that of stability of an equilibrium state. So, what is meant by this? Okay, so what is the stability of an equilibrium state? First, we need to understand what is an equilibrium state, right? Isn't it? Okay, then only we can talk about its stability, right? Isn't it not? So let us consider the state equation x dot t equal to axt plus but. Okay, so we consider the state equation of single input, single output LTI causal system. Okay, now we introduce the definition of what is called as an equilibrium state. So a state x dot is set to be an equilibrium state of this system. Of course, in any general system, right? For the system, if the state starting at x star remains at x star for all future time, in the absence of any external input, right? So external input or we can call them as disturbances or perturbation. Okay, so we don't have any perturbation or disturbance to the system or inputs to the system. Okay, the question is if the system starts at X star, would it continue to remain under at X star? Okay, so so essentially to now relook at this system, let's say we consider this whole LTE system. The state equation is X dot equals AX plus BU, right? So that's the state equation. Now, if we apply this definition, right, what are we going to have? So we essentially, just before we apply the definition, let's take an example, right? So what do I mean by this? Let's say we take a very simple example where I tie up balls using a thread and then like hang it from the ceiling, right? So this is a classical simple pendulum, right? So if I just leave it like this and there is no disturbance whatsoever, like there is no significant airflow in the room, I am not tapping the ball, right? Then what will happen? The ball will, the ball string assembly will remain vertically downward, right? So that is a very simple example of an equilibrium state. That is, the system would continue to remain in that state, like in the absence of any external input. Okay, that means u of t is not zero, and obviously, if it continues to remain at the equilibrium state at x equals x star, x dot is going to be equal to 0, right? Because there is no change, right? So consequently, in order to find the equilibrium state, X star, okay, I'm going to shorten equilibrium as EQLM dot, okay. We need to solve A times X star to be equal to 0. Okay, we need to solve A times X star to be equal to 0 to find, what to say, the equilibrium state. All right, okay. So now, if you look at this equation A x star equal to 0, right? So that is a matrix A multiplying a vector x star, and we equate it to 0. All right. So if we want to find the solution to this equation, what happens? Like there can be multiple scenarios, right? Depending on the nature of the matrix A. Okay. So depending on the nature of the matrix A, we can have two possibilities. Okay, we can, if A is invertible or A is non-singular, okay, there is a unique equilibrium state x star equals 0, right? Because if A is invertible, the only solution to what to say, A times x star equal to 0 is 0 itself. All right. So on the other hand, if A is singular, that is non-invertible, then X star belongs to the so-called null space of A. What do I mean by null space of A? Null space of A contains all vectors X star such that A X star is 0. Okay. So when A is singular, this null space of A is an infinite set. Okay. So there are going to be an infinity of equilibrium states. So in this case, we will have a unique equilibrium state at the origin. Okay, so you will hear all these terms. Okay, when you start working in this field. So I'm just writing down all the terms that we may encounter. So when people in state space representation, when they talk about the origin, they are talking about x equals 0, right? And the context in which they are talking like that is essentially to sort of like indicate that we are essentially looking at the equilibrium state to be at the origin. Okay, and we get a unique equilibrium state at the origin when the matrix A is invertible. All right, yeah, or non-singular. So when the matrix A is singular, we have an infinite set of equilibrium states. Okay, and since the null space of A is also a continuous set, people will say there is a continuum of equilibrium states. Okay, these are alternative terms that you will have. Okay, when you have the second case. Okay, because if A is singular, then Ax star equal to 0 will have infinite solution, okay, for X star. All right, as far as the equilibrium states are concerned. Fine. Okay. So with this concept of equilibrium state, with this notion of equilibrium state, that is the notion of equilibrium state is that if the system is of that equilibrium state, and if there are no external inputs / perturbations or disturbances, the system would continue to remain at the equilibrium state forever, right? So that's the notion of equilibrium state. Okay. So if we want to find the equilibrium state for the class of systems under study, we solve Ax star equal to 0, and we can have two cases, right? For X star, depending on whether A is non-singular, then we'll have a unique equilibrium state at the origin. And if A is simpler, we have a continuum of equilibrium state, right, which belongs to the null space of the matrix A. All right. So I'm going to leave you with an exercise, and we will continue from this point in our next class. So I will give you two state matrices. Okay. Please do find the equilibrium state in both cases. Okay. The first case, the matrix A is 1, 3, 1, and -2. Those are the two rows. Okay. In the second case, we are only considering second order systems, right? So consequently, the state matrix is a 2 by 2 matrix. So in the second case, the matrix A is 1, -3, 2, 1. Okay, and the exercise is that, like, find the equilibrium, okay, in each problem. Right? So there may be unique equilibrium state or an infinity of equilibrium. So the exercise for you is to find those equilibriums. So please solve these two problems. Pretty simple, and then we would continue from here in the next class. Okay. So do you have any questions about the concepts that we discussed today?
So what is the physical infinite equilibrium state?
I'm sorry.
What is the physical meaning of infinite equilibrium state?
So when you have a system that essentially has a non-singular or a singular state matrix, okay, what happens is that if you have a perturbation to the system, that system could settle down, even if the equilibrium state is stable, along any one of these, what to say, infinite set of equilibrium states. Okay, so we will discuss it when we do a few problems. Okay, we will see what will be the null space of that corresponding matrix, which is singular, and then we will try to draw some physical intuitions out of it. Okay, when we do examples. Okay. I'm sorry.
Okay, sir.
Okay, fine. All right. So any other questions? Okay. So let me stop today's class here. Thank you.